All right. What we need to start off with is talking about dot product, which is a calculation for vectors that is useful in some situations that we might happen upon throughout the semester here. And really, just let's just go with the definition, and I'm going to use a three-dimensional vector. Three-dimensional vectors, and A is just our standard A1, A2, A3, and then B vector is B1, B2, and B3. And it's really a pretty simple little calculation. A dotted with vector B, then as we just multiply the first components, A1 times B1, and then add to that the second components, A2 times B2, and then add to that the third component, product, A2 times B3. All right. Now, first question then is, when we do this, do we get a vector or a scalar out of it? We get a scalar, yeah. This is just going to be a number because all I'm doing is I'm multiplying two numbers together. You know, these were numbers, of course, starting off with. So multiplying two numbers and then adding to that product of two more numbers. Yeah, that's just going to be a number, isn't it? It's just scalar. So the dot product typically is just a scalar. It's also called scalar product or inner product. The book mentions those two as well. So just FYI there. All right. So yeah, it's pretty easy. So if I dot 3, 2, -1, dot that with 4, -5, and 6. Yeah, it's pretty easy. Just multiply the first two together. 3 times 4 is 12. Add to that then the second two. 2 times -5, so that's -10. And then add to that the third component's product, -1 times 6 is -6. Winds up with -4. Okay? Pretty simple. Now, of course, its two-dimensional counterpart would be analogous. What would we get here? If I do 4i plus 2j, that vector, dot that with 6i minus 3j. And how do, here's another question, how do I know it's a dot product? Is that the same thing as times? How do I know I just don't distribute there? It's a vector, okay. Yeah, it's just the context. You got to know the context. This is a vector, this is a vector, so there's not a times in that. It's a dot product, which is a little different. So in this case, I've got the IJ format, and it's two-dimensional. We don't have a K, so 6 times 4, or 4 times 6, you got 24, plus then 2 times -3, so that's -6. Yeah, so that'll be 18. All right. Now, that's great. That's fine. However, it's also helpful to kind of get a secondary way. We'll utilize both ways, the dot product here, but there is an alternative format or way to calculate the dot product. And it has more to do, I guess you might say, with the geometric interpretation. And so let me talk about that just a little bit. Turns out the dot product also can be thought of the magnitude of A times the magnitude of B times the cosine of theta, which theta is the angle between A and B vector. So if we we look at the two-dimensional case here, vector A and then vector B here, theta is this angle right here, the angle between them. All right. And so just to see that these two are the same quantity, let me go to another one here. Leave both of those up here. All right, so let's find A dotted with B both ways and verify that is the same. You can this actually comes out of the law of cosines. If you use the law of cosines and properties of the dot product, which I didn't mention that, properties of the dot product are very similar to just regular products, and those are mentioned there in the section. You can find those, but anyway, using those properties and law of cosines, that's where this comes out. And again, more time I would show you that, but maybe in another place. So, all right. But this will just verify that these two are the same for one particular case, and we can do it for all the others as well. So let's say we've got A is, let's just do two-dimensional, 2, 2, and B is 6, 0. All right, so our first way, A dot B, using this definition, is what? In this case, we just got 2, so the first 2 would be 12, and the second 2 would be 0, 2 times 0, so you get 12. Easy one. Now the second way, if we do it this way, it's a little harder, I guess, a little more calculation. What is, so I'm using, so I can have myself some room right here. What do I get if I go that way? Well, this is the magnitude of A. How do I get the magnitude of A? 2 squared plus 2 squared square rooted? Yeah. Square root of 8. Or 2 squared of 2. So that's 2 squared of 2. Magnitude of B, that's an easy one, isn't it? Be 6, okay. That would be 6. And then the cosine of the angle between them. And so that takes a little, not too much work, but let's visualize it here. All right, so we got 2, 2, so that would be 1, 2, 1, 2, so 2, 2 is here. And then here, 6, 0, like that. So what angle is that? Well, if you think about, just kind of think about let's do it that way. That's 2, that's 2. Well, I guess we could just figure out what this would be. If we use that triangle, this would be square root of 8, wouldn't it? Pythagorean theorem. So the cosine is 2 over square root of 2. Do it that way. I mean, it turns out it's a 45. Yeah, it's a 45-degree angle. But so it'd be 2 over the 2 square root of 2, right? Adjacent over opposite. That's what I'm doing there. Which those cancel out. The 2's do, and then the square roots of 2 cancel out. Look what it is. You got 12. Okay. So sure enough, either way you go, you get 12. And like I said, it works. It works for all such cases that we might happen upon. Now, one nice consequent or corollary to this second dot product formula and we did the two-dimensional case, but it also works in three-dimensional cases as well. But we can use this to actually find an angle between. Say we don't know the angle between two vectors. Couldn't we just solve that for cosine theta? And that we could use that to find the A dot B over the magnitudes product. Yeah. And so we get the dot product, we get the magnitudes of those vectors, and then use our inverse cosine. And this, so we can use this to find the angle between two vectors. Yeah. Okay. All right, so let's find the angle between A is 4, 5, B -1, -3. All right. So we would have what? Cosine of theta, that would be our angle, cosine of the angle between them, is the dot product. What's the dot product here? -4 minus 15, right? Because 4 times -1, -4. 5 times -3 is -15. Combine those. All right, then the magnitude of A is square root of 16 plus 25, square root of 41. The magnitude of B would be the square root of -1 squared plus -3 squared, square root of 10. So that puts the cosine at -19 over the square root of 410. So how are we going to get theta out of that? Well, theta is going to be our inverse cosine, right? Which that is then 160. I believe that's right. Okay. Wait. I get 0.352, that would be in radians. I don't know if the book prefers radians or degrees, but probably radians. Most places is. But yeah, for comparison then, multiply that by 180 over pi. Oh, sorry, that's wrong. That is not correct. Huh? I put in positive 19, so oh. Yeah, 2.7. This should be 2.7886. That would be the radians, which is approximately. That's an approximation. 775, yeah, degrees. All right. Yeah. And just to make sure we're on the right track here, if we look at this, these vectors here, 4, 4, 5 would be right there, wouldn't it? That'd be A. And B is -1, -3. It's about right, doesn't it? About right. You got 90 and then that'll be 70, 70 more. You know, you got 90 here, and so, yeah, those two in combination must be about 70. So, that looks pretty good. I'm buying it. Okay. All right. So, like I said, this can too be, that's 2 dimensions, but it works just as well for 3 dimensions. Let's do one there just to see we got the process here. All right, so find the angle between A equals I plus 2J minus K, and B 3I minus J plus 2K. So the cosine of the angle would be, it's the dot product over the magnitude of A, magnitude of B. So in this case, that would put that as what? What would be the dot product here? Yeah, so we multiply 3 times 1, 2 times -1, -2 again, so that'd be -1, wouldn't it? Then the magnitudes here, square root of 1 plus 4 plus 1, square root of 6. A, and the magnitude of B, square root of 9 plus 1 plus 4. 14, square root of 14. So we got the square root of 84. And so theta then will be the cosine inverse of that. So we could simplify that, but same drill. 92? Okay. Okay. 1.68 radians. What'd you say, 90, what? 96 degrees? Okay.